All right, welcome. We're going to go ahead and do lesson 3 here for applications of derivatives. Our two goals here are calculating derivatives and interpreting their meaning. We're going to go into some other different contexts other than velocity and acceleration today. Number 2 is identifying and interpreting these rate in, rate out problems, which again, we'll kind of talk about what those mean here in a moment. All right, so our first scenario here, we have this written out description that we're going to take a look at. Every year on the day after Thanksgiving, people rush to stores to snatch Black Friday deals. A store at the mall is having a 12-hour sale starting at 4 a.m. The total number of shoppers who have entered the store T hours after the sale begins is modeled by the function S, defined right here, for 0 less than or equal to t less than or equal to 12, so only between 0 and 12 hours. At time 0, when the sale begins, there are no shoppers in the store. So t0 in this case corresponds with the starting of our sale, 4 a.m. It's an interesting thing to note. All right, write a function that gives the rate at which people enter the store between 0 and 12 hours. So we're looking for a rate. The function we have here is simply counting out the total number of people that have entered the store, right? S of t is just number of people that have entered. It's counting them up. It's a total. If we were to plug in 5, it would give us, the answer for how many people have entered the store after 5 hours. So if we want to know a rate, we need to calculate the derivative. So we need to know S prime of t. So taking this derivative here, right, we're going to get 4 times a half there is 2t to the third minus 3 times 16, that's 48 t squared. 2 times 144 is 288 t. And so that is our derivative function, again, restricted here between only 0 and 12 hours for t. So this function, S prime of t, would give us, in terms of our units, right, it would be people entered, because that's what the units of S of t are per hour. So we know that this is a nice rate function giving us the rate at which people enter the store, right? People enter per hour. Question 2. At what rate are the shoppers entering the store at 7 a.m.? Okay, so in this problem, we want to know a specific rate at 7 a.m. A lot of people would be tempted to go ahead and say that this means t is equal to 7. That would be a relatively common interpretation. You'll often see these times situations where t equals 0 represents like midnight. But that's not what's happening here. Our sale starts at 4 a.m. and t equals 0 is when the sale begins. So that means 7 a.m. is t equals 3, because that's 3 hours after the sale starts. Again, tricky there. You want to make sure to carefully read any of your scenarios to know at what time value you should be entering in these situations. So S prime of 3, that's going to be calculated here by replacing all of these t's with a 3. So I'll go ahead and write that out. That's 2 times 3 to the third minus 48 times 3 squared plus 288 times 3. Again, I'm going to go ahead and do this calculation. I'm not going to show what I'm doing here. You can just plug that in a calculator or Desmos or something. We get 486 people per hour. Again, this is people entering in this situation. So at 7 a.m., we have 486 people entering per hour. All right. Question number 3. The rate at which people leave the store, t hours after the sale begins, is modeled by the function L. So here we have function L, which is our leaving function. And again, it is giving us a rate, the rate at which people leave the store. So in a sense, L of t is already sort of like a derivative function in itself, right? It is already a rate. It's giving us a rate, which, is kind of like a derivative up here where we have a rate function of people entering the store. Right now, we have a rate function for people leaving the store. All right, question A. At what rate are shoppers leaving the store at 7 a.m.? Okay, so we can go ahead and just calculate again. L of 3. Again, our time is 3 in this situation, right? 7 a.m. being 3 hours after the store opens, or sale starts. I don't remember which, but just like the last problem where 7 a.m. corresponded to 3. Again, that's just going to be calculated by replacing these two t's here with 3. So I'll go ahead and write that out. T squared minus 14 times 3. I needed to not write that as a t, but that's okay. We'll fix it. Okay. That's 3 squared. All right, and when we do our calculations here, we find that this rate is 120 people per hour. And this is the rate at which people are leaving the store. All right. Question B, is the number of shoppers in the store increasing or decreasing at 7 a.m.? How do you know? Well, there's sort of two things happening in this situation, and we need to determine the net effect. We know from our previous calculations that there are this many people entering the store per hour at 7 a.m., and then there are this many people leaving the store, right? So this is a positive rate for our scenario, right? They're entering, whereas this is a negative rate because people are leaving. When we compare these two values, since there are more people entering the store at this time instead of leaving, we can say that the total number of shoppers is actually increasing, right? So since S prime of 3 is greater than L of 3, which again means that the rate that people are entering at 7 a.m. is greater than the rate that people are leaving at 7 a.m., the number of people is increasing. All right. So this is our first example here of kind of a rate in, rate out situation. Here, the entering function, right, that is our rate in, and this up here is our rate out. And we're kind of putting those two things together in this scenario. All right, question number 4. Write a function h of t that gives the rate at which the number of people in the store is changing. So h of t is going to be kind of our net change. We have to consider both the people that are leaving the store and the people that are entering the store. So in general, these sort of functions are always going to be written out as rate in minus rate out. So our rate in function is s prime of t minus our rate out function, that is our L of t. And we could actually write out the rules for those functions, but to keep it sort of simple here, this is the way that I'm going to write it. And again, that's the basic idea here is rate in minus rate out. When we do that, right, we see the total change that is happening in this situation. That is the rate of change of the shoppers. Alrighty. Okay. We're going to go ahead and use our calculator. I'm going to be using Desmos, though you do want to make sure that you are able to use a graphing calculator to create these sorts of graphs. I'm going to go ahead and pull up our Desmos window so that we can look at that. Okay. All right, so we're going to have a function s of t. I'm going to create it as s of t, yeah, which was equal to 2t to the third minus 48t squared plus 288t. Okay, so that was our entering function. I know it was labeled as s prime. Just for notation's sake, I'm going to keep it a little simpler here. And then we had an L function, our leaving function, which was equal to negative plus fraction Okay, so here we have our two functions, S and L. Again, S really should be denoted as S prime, but in terms of our notation, it's a little bit easier for me to do this. So now we're going to create a new function, h of t, which is equal to the difference of those functions, the entering function minus the leaving function. Okay, and I'll go ahead and hide these other ones, and we want to make our viewing window match that which is on our page there. So if I kind of take a look at it, our y values need to go from, or x values need to go from 0 to 12. I'll overshoot that a little bit and go from -1 to 13, again, because our hours are going from 0 to 12. And then our y values, it has them going from -400 to +400. Again, I'll overshoot that a little bit and do 500s. And we'll count this by 100 as a default step. I'll get rid of my minor lines. Okay, so let me count those by 1 if we can. Cool. So hopefully we can see here, yeah, so we can see our function that's been graphed, h of t, and here is our function. So I'm going to talk about a few different ways that we could do this, right? On a graphing calculator, we could use our trace option to look at these different values at 1, at 2, at 3, 4, 5, 6, so on, and kind of create a representation of this. I am going to go ahead and take a screenshot of that and just kind of throw it over the top. But you do want to make sure that you can kind of use your graphing calculator and these functions to be able to do this same thing. Now let me go ahead and get rid of our Desmos window and go back here. So I will go ahead and bring this picture in, resize this a little bit so that it fits kind of where it needs to go here. Okay. All right. So here's our nice function. We can see we can now start to answer some of these questions about it. And it says, what do positive h of t values indicate? So again, h of t for our scenario is equal to the rate of change of the shoppers, right? So when we have a positive value, it means that we have a positive rate of change of the shoppers in the store. Another way of interpreting that is that the rate in is going to be a greater value compared to the rate out, right? When we do a subtraction, if you have a larger number minus a smaller number, right, that's going to give us a positive value. So up here, right, again, these are representing that we have more people entering the store and thus the number of shoppers is increasing. So number of shoppers is increasing. Again, the other interpretation I said there is that means that the rate in is greater than the rate out. Okay, part B, what do negative h of t values? So down here we have some negative values for our function. What does that represent? Again, the rate of change of our shoppers. So when we have negative values, that means that the number of shoppers in the store is decreasing during this time period. Again, another interpretation would be when we do this subtraction, the way that we're going to get a negative value is if the rate out is the larger value. So we have more people exiting the store compared to entering the store, thus a negative rate of change. So number of people, number of shoppers is, writing is rough right now. Number of shoppers is decreasing. And again, the way that we can kind of think about that in terms of rate in, rate out is we know that the rate out is greater than the rate in. Because when we do that subtraction, if rate out is greater, we're going to get that negative decreasing rate. Okay. Question 6. At what time, if any, is the rate at which people enter the store the same as the rate at which people enter the store, right? So if the rate in equals the rate out, what would happen with our rate of change, right? When we subtract those, if rate in is equal to rate out, that means that the rate of change should be 0. And we can see here there is a point right there where our rate of change is 0. We have 0, net 0 change in the store. Now, that doesn't necessarily mean that there are 0 people entering and 0 people leaving. It means that these two rates have balanced out. There are an equal number of people coming in compared to people coming out. And, if we do an approximation here, I believe if I go back to the Desmos, it's around 5.54. 5.545. That's the time that this is happening when we have a rate of 0. Again, how do we know this? If rate in equals rate out, then the number of people in the store is not changing. And we've already sort of talked about why, but again, just reiterating that, right? Let's just create something in our mind thinking about this. Let's say there are 100 people entering the store per hour and 100 people leaving the store per hour. If those rates are equal, the 100 people entering are offsetting the people leaving, right? Thus giving us that overall rate of 0. Okay, let's go ahead and move forward. So a couple things that are very important about these sort of rates of change. If we start with some function f of t, again, it doesn't have to be f, it can be any sort of function, f prime, the derivative is always going to be the rate of change of our function. So if we remember back to our problem, right, we had a function s of t that represented the total number of people that have entered the store, and then s prime of t was the rate of change of that function, right? How were the people entering the store changing? Then we have 3 important things that we always look for when we're looking at derivatives. We often want to know when is the derivative equal to 0, right? When is our rate of change equal to 0? Because that means that our function is not changing, right? There's no change. We want to know when is our function greater than 0, right? That's another way of saying positive. Greater than 0 is positive. That means our function is increasing. And we want to know when is our derivative less than 0, right? That's another way of saying negative. That means our function overall is decreasing. So again, just in terms of interpreting that previous scenario, right? We looked and saw when the net change, that h of t function, when it was positive, when those values were up above the x-axis, right? It was something like this, like up above the x-axis and then down below it. In this region, we had positive h of t values. So we had a positive rate of change. And then down here on this part of the graph, we had negative h of t values. So we knew that it was decreasing. Whereas right in this middle section right here, right, where the value was 0, that was representing no change. Just trying to re-establish that to the context that we just talked about. Anyway, please make sure you try those check your understanding problems, and I'll see you next time.